students, welcome back to my system design series, and this is lecture number 24 where we are going to discuss problem caused by replication lag. If you haven't watched the previous video, then kindly watch it so you will understand what do you mean by replication lag. Okay, so in this video, we are going to discuss these topics. Okay, so let's get started. Out of all the problems, read your own writes is one of the problem which is caused by replication lag. You write something to the system and immediately when you look it is not there. Wait, what? You just added the data and it is not available. In a non-replicated system, this wouldn't happen. You will always see what you have wrote. But with replication lag, it can happen. Okay, let's understand this. You wrote to the leader, then perhaps the next operation is to read. That ended up being served by the followers. But that follower haven't got that right data. So the follower's response doesn't include your new data. It is as if your write never happened. From that follower's point of view at that moment. This inconsistency window might be tiny, but if your app tries to read it at that unlucky moment, then the user have to suffer. Classic scenario is user sign up. Suppose a user creates an account. These rights are passed on to the primary database. Right after that, the app automatically tries to log the user in or fetch the profile. If the read goes to the replica, that is a step behind. It might say the user is not found because that replica haven't got the details about the new user. That is the read your own write consistency failure. The user is like, I have just signed up, then why I am not found? Is the system broken? From the system's perspective, nothing is permanently wrong. A moment later, the replica will have that user. But that one moment have caused the bad user experience. This problem is called read your own rights issue, read after write consistency issue. From the developer's perspective, these issues mean certain flows can break. For example, some database or API calls might have written the data first and then immediately do a read, maybe to confirm or to get some calculated result. If the read hits the replica, it might get the stale data. This problem is obvious in multi-node system. So, read after write is often a desired guarantee. That is, it ensures that clients can read their own updates. Many systems implement some tricks to achieve that even with replication. But as of now, we are just discussing the problems. If the replication lag exists, a user may not be able to see its own writes immediately, which is causing the confusion. Okay. Second is non-monotonic reads. Alright, this is slightly more subtle one. That is a non-monotonic reads or out of order reads. Fancy term, but I can explain simply. Okay, what do you mean by monotonic? Monotonic means things move in one direction and don't move backwards. In the context of reads, monotonic reads means if you observe some data at one point, any subsequent read will not show you the older data then, or put in another way, your knowledge of data should only move forward, not in backward in any time. Non-monotonic reads is when that gets violated. You might see the newer data and then you see the older data, which feels like the time went backwards. This can happen with the replication lag when you query different replicas at different times. For example, at 10 o'clock, you make a query to replica A. It is up to date and returns the data that includes the recent update. But at 10:05, you hit the query again and it will hit to the replica B. Suppose the replica B is a bit behind and has not got the update yet. It returns the data reflecting it in earlier state. Imagine you have opened the Amazon application and want to inquire about the product which you have ordered. And in terms of this discussion, if the query hit to replica A, it will show that your product have been shipped. But after 5 seconds, you again hit that query and it will go to the replica B. And now you saw that the product is still not shipped. You will feel confusing. This violates monotonicity because your second read was older than your first read. This can also happen not just with the same data item but with related data across queries. A practical case described by engineers of Shopify goes like you perform one query to get the list of items from table X. And then another query from another table Y to get those related data items. If two queries goes to two different replicas with different lag, you will get the mangled result. The list from query 1 might include the items which the query 2 might find it. From the user's perspective, Non-monotonic reads are confusing and can be worse than single stale read. It reduces trust because the system appears to contradict itself. 1 second it shows something, in the another second it is gone. Monotonic read consistency is usually we take for the granted when we are dealing with the one database. If I did query A, then immediately I did query B, I expect the same results from both of them. In distributed replicas, you have to work more to ensure this kind of situation doesn't happen. Let's discuss cross-device or cross-session inconsistency. This issue is basically the variant of read your own writes, but spread across multiple devices or sessions. Imagine you are using application on two devices. Say your laptop and another is on your phone. Many of us do, right? Maybe you are using Instagram or WhatsApp or any other application, one on web, that is on computer, another on the application in your mobile. We expect that when we do something on one device, it reflects on another device pretty quickly. When it doesn't, the replication lag is the problem. Cross-device issues are aggravated by geo-distributed systems. Often, companies route your request to the nearest server or data center. If you are traveling or your devices are in different region, imagine you are using VPN on one device or one device is on mobile network that connects differently. You might hit different regional replicas. For example, your phone might be connected to the US data center and your laptop hits the Indian data center. Your write went to the US data center and when you are reading it, it will read from the replica of Indian server. And this replica is little behind, so it will lag. This is essentially multi-region replication scenario. Instagram actually faced this when they moved their data centers into multiple regions. For example, when the comment made on one region, it was not immediately reflected on one of the follower which is in different region. They solve it by ensuring the other region's cache gets invalidated. So it fetches the new data, but there is inherently slight delay in the propagation. This can cause the confusion between the users if they switch the devices frequently. It can be mitigated by application design, like actively pushing the updates to all the devices via notification or by ensuring consistent reads across all the devices. But by default, the naive replication can cause this. The above three ones are specifically main mentioned ones. There are other couple of side effects worth noting, though they stem from the same causes. Let's look at them. First is stale data usage. If a service uses slightly stale data to make decisions, it could do something wrong. For example, an inventory site just like Amazon is showing the inventory count. If one replica has not seen an item just sold out on the primary, it might still show one left in the stock and allow other users to order, leading to an oversell situation. Okay, second is inconsistent state across components. The Shopify example we just discussed might fall under this. Pieces of data that should be consistent with each other might not be due to the queries going to different lagging replicas. It can lead to temporary violation of constraints like showing the record without its related record. If not handled, it could even cause the app errors if code assumes something exists just based on the previous query. Okay, let's move forward. The third is cache coherence issue. If you have caching plus replication, sometimes cache doesn't know what are the updates happening in the another region right away. Instagram's comment example is basically based on this. Each region has its own cache, and a comment in region A doesn't invalidate the comments in the region B's cache until the mechanism is put in a place. Users might still see the stale cache content from another region until invalidation catches up. Now, none of these problems are unsolvable. Big systems have developed techniques and patterns to avoid this pitfall while still using the replication. The key is to be aware of where strong consistency is needed and implement something to get it, or to design the user experience to tolerate the eventual consistency gracefully. We have seen how replication lag makes the data act funky, missing writes, time traveling reads, one device out of sync with another. But engineers have the bag of tricks to tackle this issue. Next, we will go through how systems like Amazon, Instagram, WhatsApp solve or mitigate these problems. Okay, let's talk about Instagram and Facebook. Instagram is a great example because their team has openly talked about their multi-region setup. Initially, Instagram was running on one data center. As it grew, it moved to multi-data center architecture. If you want to read further, you can find the blog in the description. They found that the data has to be replicated across region. Say one of the East Coast and one of the West Coast. They chose an approach where one region is primary for writes, others are secondary. This naturally meant eventual consistency across all data centers. If a user from region A have posted a comment, a user who is living in region B might not see this comment immediately. However, if the user A and user B both are living in the same region and one data center is serving them, then the user B will be able to see the comments of user A. This is exactly the cross-region lag issue which we have just discussed. Instagram's solution was to use a queue to propagate cache invalidation event to other data centers. When a comment is posted in primary region, they insert an invalidation entry. That entry replicates along with the comment to other regions, telling it to invalidate the cache for the photos comment. Then the next read will fetch the fresh data, which by then includes the new comment. This way they reduce the window in which the second window will show the stale data. Still a tiny lag is there, but it seems acceptable. Facebook has the same challenges with the news feed. Facebook's data eventually spreads through a cache cluster and database replicas. They actually embrace the lots of eventual consistency in the feed. If two people loads the feed a few seconds apart, they might see slightly different things. Facebook tries to maintain the session affinity in their read pools to get monotonic reads. But when something slips, you have to face the odds. Okay, let's talk about the Amazon. Amazon uses lots of distributed system under the hood. A famous story is Amazon's Dynamo. It is a NoSQL database which is created by Amazon which has been used by lots of systems. Dynamo was used as shopping cart service among others. It is an eventual consistent store. Why would Amazon chooses eventual consistency for something like a cart? Because they prioritize the availability. You should be able to add the products to your cart even if the servers are down or slow, rather than failing the operation. Dynamo would allow some inconsistency but has a mechanism that will merge and reconcile. One effect is that sometimes if there's a glitch, you might briefly see a cart item duplicated or not present, but eventually it sorts out. So on Amazon, after you place an order, you get a confirmation page, right? And your orders list that is fetched from the source of truth, that is from the leader. But if you want to query through a different channel immediately, maybe that channel's data is catching up. Okay, let's talk about the WhatsApp. WhatsApp is interesting because initially WhatsApp messages were only on your phone and the phone was primary and WhatsApp web was just mirrored via phone. In the new multi-device architecture, WhatsApp uses a server as intermediary, but each device has to get all the messages. So, if your phone and laptop both are online, when you send a message from your phone, the server gets it and forwards to the laptop. Usually it's very instant, but if your laptop gets disconnected, it may not get the message until later. From the perspective of the laptop, the messages eventually sync. That is eventual consistency again. It is not replication lag in database sense, but conceptually similar effect among the user. WhatsApp likely use some sequence number, so even if messages arrive out of order, they can be placed correctly. Consistency issues in these apps are mitigated by the UX. For example, WhatsApp uses single tick and double tick next to the message. One tick means the server has received the message and double tick means the other user's device got it. If you see only one tick mark, that means the message has not reached to all the endpoints. That is the form of showing eventual consistency state to the user. So they understand the delay. Okay, so that's it for today's video. We have saw the issues caused by replication lag and how this big systems, WhatsApp, Amazon, Facebook uses different techniques to overcome this. If you are still watching this video, then make sure you leave the thumbs up and subscribe to my channel because it will motivate me to make more videos. And thank you so much for watching.